In today's lesson, we're going over section 7.1. It's exponential functions with growth and decay. So we're going to start off with an example just to give you an idea of how quickly something grows in exponential growth and decay. So in this situation, we have someone that knows a secret, and they're going to tell two students. And then each student is going to tell two more students the secret. So we want to know how long it will take for the entire class to know our secret, how long for the entire school, and so on. So to begin this diagram, we start with one teacher telling two students a secret, okay? Then those two students tell two more students. So now we have a total of 4 new people knowing, but everyone knowing in total would be 4 plus the original 3, so we have 7. Now each of these students tell 2 more students. And now we have a group of 8 new students knowing on top of the 7 that already knew. And then we would keep showing that these students now each tell 2 more. And I am definitely running out of room. And if we're being realistic, I think that people would be telling more than 2 people this. And if we're talking about social media, this is how things go viral, because all you have to do is click a button, and it's not just 2 people that see it, it is everyone that you're friends with or anyone that's following you. So we can see how quickly rumors get started, secrets get told, information is passed. So we're going to go ahead and make a couple columns here. We're going to talk about the row number. So when I talk about the row number, this is my initial row. So I'm going to call it row number 0. This is our n value. And then we're going to have our first row, our second row, our third row, and our fourth row. How many do we have? 1. All right, so 0, 1, 2, 3, 4. Yeah, we have 4 rows here. And we'll make another column. We're going to have the number in each row. And in my first set, in row 0, the initial, we have 1 person that knows, okay? And in the second one, we have 2 people that know. In our third row, we have 4, and it doubles to 8 in our third row, and it doubles to 16 in our fourth row. Now, that's just how many people know in each row. How many people know in total? Total number. Well, in my first set, only 1 person knows. That initial set of students, now we have 3 people, the 2 students and 1 teacher. And so what we're going to do is we have 4 new people plus the 3 people that knew before, so we have 7. We have 8 new people in the third row plus the 7 that knew, so there's 15. We have 16 new people here that we're going to add up with all of the others, and so that gives us a grand total of 31 people that know. So we're going to use this idea that every time a new group knew, it doubled. So if I want to write an equation, I have a base of 2, because every time the rumor got told, 2 new people knew my rumor. And then we're going to have a power of n plus 1, n being the row number. So the initial was that only the teacher knew, no students knew. So it'd be 0 plus 1. And then to make it fit our pattern, we're going to take 1 off of that total. So this is my exponential equation. And so if we want to test this, let's go ahead and do 2 to the third plus 1 minus 1. Now if we're putting this in a calculator, you want to put that power in parentheses or just simplify it to 2 to the 4th minus 1. Now 2 to the 4th is 16, and we would take 16 minus 1 and we get a total of 15. Okay, so in the third group of students that know, we get 15. So when n is 3, we have 15 total people knowing, and we can see that works. So there's 8 new people, which gives us a total of 15. So using my exponential equation that we formed, and we did this pretty quickly, we're not going to focus on having more than one thing in the power. But on this initial equation, we can now plug in and see what happens when 5 groups of students know. I know when there's 5 groups of students, these 16 people are going to double to tell 32 more people. And if I add the 32 new people plus the 31, I get a total of 63 people knowing the secret. So if we want to test our function, we would take 2 to the 5 plus 1 minus 1. Well, that's 2 to the 6 minus 1, and I get 64 minus 1, so I get a total of 63 people that know it after 5 groups have been told. Okay? So let's go ahead and move on to another idea. And I will try to make sure that my paper is showing the whole time. All right, so now we're talking about bacteria. We have good bacteria and we have bad bacteria in our systems, okay? And if you're ever taking an antibiotic, it wipes out all the bacteria. And so you have to be careful because the good bacteria are also gone, and we need those to help protect us. So most bacteria are not harmful and they're helpful. Yogurt has bacteria. There's lots of food with bacteria. So we want to watch how quickly bacteria reproduce. So we are dividing the bacteria. The number of bacteria at any given time is referred to as a population. So that's the amount that exists, the population. When each bacterium in a population of bacteria divides, the population doubles. Okay. So our activity to look at is we're going to model a growth of 25 bacteria. This is important because the 25 is our initial amount. That's how much we're starting with. That's our initial amount. And then the bacteria is going to double, and it's every hour. We want to be careful because it could be every half hour, it could be every minute. So we want to be careful how our time is working. We might be talking about a population of people, and that could be every year or every decade. All right, so we're going to start with 0 time and 25 bacteria. So that's what we're starting with. So you touch a piece of bread and you put 25 bacteria on it with your fingertip. And then we're going to look at every hour how much new bacteria is on that bread as it's doubling. So we look at this, when no time has passed, we start with 25 bacteria. Or maybe you have a Petri dish with 25 bacteria on it. In the first hour, it doubles to be 50. And the next hour, it doubles to be 100. Now these 100 divide, and so they split. Now I have 200. And this divides, and I get 400. And those 400 divide to give me 800. And we're just going to add on one more row. In 6 hours, we would have 1,600. And we can keep going. The problem is, if I ask you what happens in a day, in 24 hours, you would have to keep writing this out till you hit 24 hours because we don't have a function. So in this problem, we're really going to explore and derive how we get our function. Okay? Then after that, you guys will know how to build a function from just being given this information and not having to create a table. All right, so the first thing we're going to do is we're going to write an algebraic expression that represents the population of bacteria n hours, after n hours. Okay, the hint is to factor out the GCF from the population. All right, we started with 25, so I'm going to rewrite this as 25 times 1. And then this would be 25 times 2. So I'm taking the 25 out of each one, and I'm writing it as 25 times something. This would be 25 times 4. And this would be 25 times, and we would just double it. Are you noticing that the 1 doubles to 2, and the 2 doubles to 4, and the 4 doubles to 8? And this would be 25 times 16, and here we'd have 25 times 32. And if we go to our extra one, we'd have 25 times 64. So if you want to double check this, just take 25 times 64. You should get out your 1,600. Okay, we're going to take it one more step. But what I want you to see is that initial population is here each time. And then do you see that this number is doubling every time to get the 200, doubling to get 400. I want to write these as a base of 2. So I'm going to keep my initial amount of 25. I want to make it times 2 to the power of 0. Okay, why am I using a 2? Because it doubled every hour. Didn't you see that this doubled every time? Now I'm going to write this as 25 times 2 to the first. Now 2 to the 0 is 1. There it is. 25 times 1. 25 times 2 to the first is the same as 25 times 2. So if I want to rewrite this as 25 with a base of 2, my power is 2 because 2 squared is 4. How do I get 8? 25 times 2 to the third. And now if you're taking a minute and looking at this, do you notice that the power is the time in hours? The power is 1, the time was 1 hour. The power is 2, the time is 2 hours. The power is 3, the time was 3 hours. I have built our first exponential function, okay? This would keep going. 25 times 2 to the 4th, 25 times 2 to the 5th, and we can check this one with 25 times 2 to the 6th. So let's go ahead and test that out in our calculator. So I've got my calculator here, and I'm going to take 25 times 2 to the power of 6. And so if I'm correct, I should get 1600. Now I can take anything, any hour, and put this in here. I could find out what happens in 24 hours, how many bacteria I have. So I have created my first exponential growth function. So what we have here is the initial amount was 25 times a multiplier of 2, because it was doubling every hour, to the power of t. And t is important to define. It stands for the number of hours. T standing for time, which is number of hours. So here is my exponential expression. 25 is my initial amount. It was doubling every hour. And so we want to find out what happens in 10 hours and what happens in 20. So if t is 10, I'm going to plug that in. 25 times 2 to the 10th. If t is 20, we're going to plug that in. 25 times 2 to the 20th. And this is definitely something that I want to be using my calculator for, as much as it is good to use your brain. So we're going to type in 25 times 2. You don't have to have the parentheses there, to the power of 10. And that gives me 25,600 bacteria in 10 hours. All right, I'm going to go back up. I'm going to change out my 10 with the 20, and that gives me a much larger number. Oh, I put my comma in the wrong spot. Put a comma there, put a comma there. All right, that gives me 26,214,400 bacteria. And that is in 20 hours. So we can see how quickly this bacteria is growing. And remember, this hasn't even been a day yet, okay? So we went from 25 bacteria in 0 hours to over 26 million in less than 1 day. All right, so let's take this to the next step. We have the same idea, and this time we start with 75 bacteria instead of 25. Okay, so we still have that the bacteria is doubling. So the only thing that changes in my expression right here is I start with 75. It's still doubling every hour, and T stands for, again, time in hours. So number of hours. So I would put in when the time is 10, I'm just going to put a 10 in there. So it would be, T is 10, we get 75 times 2 to the 10th, and we're going to come back and also look at that in 20 hours. So go ahead and type that in a calculator. You'll get 76,800 bacteria, and that is in 10 hours. And you'll get 78,643,200 bacteria, and that is in 20 hours. So we can see that these numbers are increasing quickly. And when you started with the 75, we definitely have a much bigger number, from 26 million to 78 million when we started with 75 in the same time span. And this is why we wash our hands.
Whoa.
All right, so now we're going to focus on what we are looking at and what we are working on in this Algebra 2 level. We're going to talk about growth and decay that can be modeled using a function with a variable as an exponent, and that's what makes it exponential growth or decay. We have a variable and our exponent. This function is also known as an exponential function. The parent exponential function is f of x equals b to the power of x. And b is your base, which is a constant, and the exponent x is your independent variable. That's what we're going to put in, and we're going to get y, or f of x, out. The base of an exponential expression is commonly referred to as the multiplier. So this is your parent function. But I like to remember in a little bit more of a simple term. So when we look for exponential growth or decay, we're going to talk about the initial amount, what you're starting with. The initial amount could be a population. If we're talking about bacteria or people or animals, the initial amount could be money, how much money you invested, the initial amount that a car or a house was worth, okay? The initial amount can also be something about medicine, how many milligrams, what was the peak amount. So initial amount is anything starting. If we're talking about money, a lot of times it's called the principal, what you started with. And then we're going to take that times the multiplier. The multiplier is what is happening to that initial amount or that population. The multiplier is doubling, it's 2. If it's tripling, it's 3. But if it's growing or decaying by a percent, we have to talk about how to create that multiplier. And then we're going to put it to t, and t stands for time. And again, we have to be very careful with t. T could be hours, it could be half hours, decades, minutes, years. It can be anything that's defined, so you want to be careful with what they're giving you as t and what it's defined as. Now I want to talk about this multiplier a little bit more, so I'm going to go up here and talk about the multiplier. When you have growth, and this is going to make a little more sense as we move through problems, but when you have growth, you're always starting with 100% of what you had plus more, okay? Just like tax. You start with 100% of your bill plus 6% sales tax. So we have 106%. So growth is always going to be 100% plus what you're increasing by. Decay, when you're losing something, when it's going away, decay is always going to start with what you had at 100%, and you're going to take away that percent. So if you're losing 20%, I'm not as interested in what you're losing as what you have left. So growth is always going to be 100% plus, decay is always going to be 100% minus, and the multiplier should always be in decimal form. All right, so if you're given a percent, we're always adding or subtracting to 100. If your multiplier is doing something like doubling, if something is doubling, if it doubles, it is going to be a multiplier of 2. If it triples, it is going to be a multiplier of 3. And that 2 really comes from 200%. That 3 really comes from the idea of 300%. If something's doubling, you have the initial 100% plus another 100%, and that would give us 200%, which shows that it doubles. All right, so these are good notes to have, and they're going to make some sense as we go back through. So here's another situation for you. The human populations grow at a much slower rate than bacteria. All right, bacteria that double every hour have a growth rate of 100% per hour. So what we have, 100 plus 100, 200%, it doubles. The population of the United States in 1990 was growing at a rate of 8% per decade. Okay, so not only is the 8% important, but it's per decade, and that's very important. So the initial population in 1990, so this is your initial amount, your initial population. In 1990, it was projected to grow at a rate of 8% per decade, just what we saw. Predict the population to the nearest whole number in the years 2010 and 2025. All right, the first thing we want to do is find the multiplier. So I'm going to have 100% of my population plus 8. That gives me 108%. And if I want the multiplier in decimal form, I take 108%, I divide the 100% out, and I get 1.08. This is my multiplier. If you think about multiplying by 1, you get your initial amount back plus 8 hundredths, which is 8%. write an algebraic expression to represent this. My initial population was 248,718,301. I'm going to multiply that by my multiplier of 1.08 to the power of time. And the time is important to note that it stands for number of decades. So we can see the use of the initial amount, the multiplier, and the power of time. All right, now in this question, we want to find out the population in the year 2010 and the year 2025. So in the year 2010, from 1990 to the year 2010, that is 20 years. When I go to put that 20 years in here, I need to write it in decades. So 20 years gives me a T that is 2 because it is 2 decades. So we want to be careful not to put the 20 in here. So I definitely want a calculator to do this. I'm going to write it out, my initial amount. I want to be careful when we type these large numbers in our calculator, times my multiplier of 1.08 to the power of 2. Again, please don't put a 20 in there, it's 2 decades. We type that in and we get a total of 290,105,026 people, and that was in the year 2010. That was the prediction for the year 2010. If we go from 1990 to the year 2025, that is 35 years. But again, T would be 3.5. Remember, we have 10 years in every decade, so we're simply dividing by 10. So we put this into our equation again. Times 1.08 to the power of 3.5. And we end up with 325,604,866 people, and that was the prediction for the year 2025. Now population rates change, and so this is in old statistics with old predictions, and so we could go back and we could see how accurate these predictions were and how much the growth rate has changed. Continuing on with a similar example, we have a problem about the population of Brazil. So here is our initial population, and that's in the year 1996. It's projected to grow at a rate of 7.7%, and again, it is per decade. We want to predict the population to the nearest whole number for the Brazil in the years 2016 and 2020. So again, we want to build our exponential equation or exponential expression by taking our initial amount, 162,661,000 people. We need to find our multiplier to the power of time. Our multiplier is coming from that 7.7% per decade, and again, it is growing. So we would start with 100%, and we would add 7.7%. And the reason I like to put this in the percent form is because sometimes the decimals, we see it differently than it is. So if I have 100% plus 7.7, that's 107.7%, just under 108%. When I use this as a multiplier, I move decimal twice by dividing by 100, so I get 1.077. Again, this is just below 108%, which would be 1.08. So we want to make sure we're not writing it as 1.77. That'd be a 77% increase. So we'll put in our multiplier of 1.077 to the power of t, and again, t stands for the number of decades. So we want to be careful with our time that we are using it correctly. So what do we want to do a prediction for the year 2016 and another prediction for the year 2020. In the year 2016, t is going to be 2 because that is 20 years, which is 2 decades. And so we will put in our equation, our 162,661,000 times our 1.077 to the power of 2. And with that, we get a total of 188,661,000 675,211 people. And that is in the year 2016. All right, in the year 2020, it is going to be 2.4 decades. The year 2020 is 24 years from 1996. So both of these from 1996 to 2016 and 1996 to 2020. And so again, we're going to write out that initial population times our multiplier from the 7.7% to the power of 2.4, as it's 24 years, 2.4 decades. We get a grand total of 194,357,420 people, and this is in the year 2020. So there's another population problem. All right, we're going to go ahead and continue practicing some problems. This time we're talking about a stock market or a stock company. So we have someone who's investing $1,000, that's the initial amount, and it's at the end of 1999. The value of the stock increased at a rate of 15% per year. We want to predict the stock to the nearest cent at the end of the year 2004 and 2009. Okay, now this is being a very, very simplistic problem, not indicative of a true complex stock market. We're just averaging a 15% growth per year. And again, these are some older numbers, so it's not something that we see right now, a 15% increase. But still, we're going to start with this, and we're going to do V of t. I'm going to go ahead and change this up and make it the value over time, or maybe you do the amount over time. So I'm going to put it in function notation, and that is equal to the initial amount of the $1,000, and the multiplier is 1.15, and that came from having 100% of the money invested plus 15%, and that gave us 115%, which is 1.15. And if you really think about this, we multiply by 1, we get our $1,000 back, plus another part of it coming back in interest. That's what we're getting. If you were doing an investment and money in an account, you'd get interest. This is the 15% that our stock is growing. So we're sort of getting that back on top of what we invested. And we're going to go to the power of t. So what is the value of my stock in the year 2004? Well, we're starting in 1999, and the year 2004 is 5 years later. So in 2004, t is going to equal 5. And so that gives me the value over 5 years is going to be my $1,000 times 1.15 to the power of 5. If we put that in our calculator, we find that the value over 5 years is $2,011.36. So I'm going to go ahead and label that $2,011.36 in the year 2004. Now that's not too bad for having an extra $1,000 and letting it sit for 5 years. You can over double your money if you have a rate of 15% growth. And the year 2009, well, that is 10 years. And remember, we're going by years. It's per year. And so I'm going to do V, the value of the stock over 10 years is 1,000 times 1.15 to the power of 10. That gives me a value in 10 years of $4,045.56 in the year 2009. Now, we'll come into some lessons when we get into compound interest. That how the money is growing on money also. Okay, so your investment is not just growing on your initial amount, but the money's being put back in. So we'll talk about how quickly money can grow. All right, now this one's a different problem. We are no longer increasing, we're actually eliminating. So you have a caffeine drink or a medicine that has caffeine in it, like Excedrin, anything with caffeine, coffee. So you have a caffeine intake, and it's eliminated from your bloodstream as an adult at a rate of 15% per hour. Okay, so once you hit your peak amount, you're losing 15% of that caffeine out of your system, out of your bloodstream every hour. So an adult drinks a caffeinated soda, and the caffeine in his or her bloodstream reaches a peak of 30 milligrams. Okay, so this is my initial amount. When we hit the peak level, that's what we're talking about, the peak level. Predict the amount to the nearest tenth of a milligram, we want to pay attention to detail, of caffeine remaining. This is important. 1 hour after the peak level and 4 hours after the peak. So everything's based on the peak level. So my initial amount, so we're going to do the amount over time, okay? My initial amount of caffeine is 30 milligrams. I need a multiplier, but guys, this is eliminating, which means it is decay. So we have 100% of this caffeine in our system when we hit that peak level, and we're losing 15%. My multiplier is not what I'm losing. My multiplier is what is left. And 85% is what is left in my system. And as a decimal, it's 0.85. And so that's where we want to be really careful. When something is decaying or being eliminated, we're not worried about what's leaving our system. We want to know what is remaining in our system. So if they give you what's being eliminated, you want to turn it around and make sure you know what is left. And then we're going to do the power of T, and time stands for number of hours. All right, so when I find this in 1 hour, the amount over 1 hour of time is going to be 30 times 0.85 to the power of 1. And if we put that in there, after 1 hour, you have 25.5, nearest tenth, milligram remaining after 1 hour. So 25.5 milligrams of caffeine after 1 hour. All right, after 4 hours, we have 30 times 0.85 to the power of 4, which gives me 25.5. Sorry, I'm just copying that down. So we put this in our calculator. We're going to get less. We're decreasing over time. After 4 hours, we get 15.7 milligrams of caffeine remaining after 4 hours. We have two final examples here to keep practicing our exponential growth and decay. So this one is similar to the caffeine. We have a vitamin and it's being eliminated from the bloodstream at a rate of 20% per hour. Okay, so remember, it's being eliminated, so we're talking about decay. The vitamin reaches a peak level in the bloodstream of 300 milligrams. So this is our initial amount. Predict the amount to the nearest tenth of a milligram of the vitamin remaining. We want to know what's left 2 hours after the peak level and 7 hours after the peak level. So we're going to start out with maybe the amount over time. So I'll do A of T, the amount over time, is equal to 300 being the initial amount. That's our peak level, is our initial amount. And then we're going to take it times a multiplier of 0.80 to the power of time. That multiplier came from the idea that we started with 100% of the peak level and we took away 20%. That gives me 80% left. 80% is remaining in my bloodstream or the person's bloodstream. So if 20% is being eliminated, we know that 80% is remaining, and it specifically asks for the amount remaining, not how much has left the bloodstream. And so that gives us a multiplier of 0.80. So I want to remind you, if it's growth, we add it to 100. If it's decay, we take it from 100. So your growth will always be 1 point something, but your decay should always be between 0 and 1. All right, so we want to find out what happens 2 hours and 7 hours. So A of 2, so the amount after 2 hours would be 300 times 0.80 to the power of 2. And if we throw that in our calculators, we get the amount after 2 hours to be 192 milligrams after 2 hours. That is what is remaining. All right, we're going to come back with A of 7, and that would be 300, the initial amount, times 0.80 to the power of 7. So the amount after 7 hours is going to be 62.9 milligrams after 7 hours. So that is how many milligrams of the vitamin are remaining after 2 hours and after 7 hours. And I always recommend that you do put these in the calculator just so you understand how to put them in correctly. If you put it in the calculator, it knows the order of operation, so it will do your exponent first and then come back and multiply. If you're doing the parts, you want to make sure again that you do your exponent first, your power, before you multiply. You are not taking 300 times 0.8 and then the power. So power first and then multiply that outcome by 300. All right, one last example on creating these. We have a car that's being bought for $15,000. So that's our initial amount. That's what we're starting with. And that, for sometimes it's the principal if you're starting with that money. In this case, it's the amount, the value of the car. And the value of the car is decreasing at a rate of 8% per year. So decreasing meaning that we're talking about decay. Predict the value of the car to the nearest cent or penny after 4 years and after 7 years. So the amount or the value of the car over time is going to be an initial value or initial amount of $15,000, and it's decreasing at 8% per year. So I'm going to take that 100%, the value of the initial car value, and we're going to take away 8%. And that leaves us a 92% remaining at the end of the year. And so that 92% is going to be a multiplier of 0.92. So plug in our 0.92 to the power of t. And I do want to keep defining that t is the number of years. And I did forget to define t up here. T stood for the number of hours. Okay. So we want to find out what happens in 4 years. So how much is this vehicle worth in 4 years? Now we're doing a straight depreciation. In real life, when it's a new car, brand new, it depreciates as soon as you drive it off the lot. And there is a definite depreciation every year. And then when your car is so old, it sort of levels out and it might be worth a couple thousand. So it is not a straight line depreciation in real life, but for our purpose, we are using that it is depreciating at 8% per year average. All right, so the amount over 4 years, we'll make this into a 4 there. The amount over 4 years is going to be $10,000, $745.89. That's how much it is, that many dollars after owning the car for 4 years. All right, the amount over 7 years would be your initial $15,000 times 0.92 to the power of 7. And so that'd be the amount over 7 years is going to be around $8,000, $8,367.70 after 7 years. Now, if we kept going with this and we found the amount after 10 years and after 20 years, you're going to see that the amount is definitely decreasing, but there's always a little bit left because we're taking 92% of what's left. So the amount that the car is decreasing, the value is decreasing, is going to start leveling off. The next thing we'll look at with exponential growth and decay are graphs.